Welcome to the Explainer. If you're taking on the Cambridge IGCSE physics examination, specifically paper 0625, you are looking at a really serious challenge. It's tough, and sitting right there in the middle of it, popping up in literally every single exam series, is the often misunderstood concept of induced current and Lenz's law. Mastering the idea that the direction of an induced electromotive force, or EMF, always opposes the change causing it, along with the relative directions of force, field, and induced current, well, that is absolutely essential if you want top marks. So today, we're doing something a bit different. We are combining ancient warrior wisdom with modern exam strategy. Our goal? To help you learn how to slice through these complex physics questions with absolute pinpoint precision.
Okay, let's dive into this. Why is it that incredibly smart students who really know their stuff, just hit a total brick wall here? Well, the raw physics knowledge is usually there, but the incredibly strict phrasing that Cambridge requires just fractures it. Let's look at two theoretical students. We'll call them Alex and Sam. They actually represent the two massive traps that students fall into the second that the timer starts ticking. Now, they both study hard, right? They both know what a magnet is, they know what a coil is, but they fall apart in very, very different ways. And honestly, you might even recognize a little bit of yourself in one of them. Our goal today is to validate those struggles, dissect exactly what's going wrong, and give you the ultimate framework to just bypass their mistakes entirely. Here is our examiner's playbook for today's explainer. We'll start with core principles, move into our procedural framework, tackle critical analysis, and wrap up with the top examiner warnings. Let's get right into it.
Section 1. Core Principles. Let's master the fundamentals of induced current.
Now notice how perfectly these two profiles capture the extremes of exam panic. First, we have Alex. Alex's strategy is what I call the knowledge dump. Seeing the words induced current, Alex completely panics and just writes down every single physics fact they can possibly remember. They overload the answer with raw facts, but there's absolutely no critical analysis. They aren't actually answering the specific question being asked. Then, on the other extreme, we have Sam. Sam is just constantly fighting the clock. Sam rushes, scribbles down a super brief three-word answer like current goes up, and completely misses the command word requirements. If the examiner's command word is explain, Sam just states. And guys, both of these approaches just bleed marks. Top-performing students don't just dump facts, and they definitely don't rush through. They exhibit a connected conceptual understanding of these principles. So the absolutely crucial starting point is getting our definition straight. Lenz's law explicitly dictates that the direction of an induced EMF always opposes the change causing it, and this is all governed by the relative directions of force, the magnetic field, and the induced current. Cambridge examiners are desperately looking to see if you understand that these three exact vectors are inextricably linked, literally at right angles to each other. Think about it like this. When a magnet falls through a coil, that coil doesn't just sit there and passively accept it. No way. The induced current actually creates a magnetic pole that actively fights the magnet's motion. If a north pole is falling towards the coil, the top of the coil becomes a north pole to repel it. That, right there, is the opposition that Lenz's law is talking about. Grasping these relative directions is the absolute bedrock of every single mark you're going to earn in this topic.
But here's the catch. Just knowing that definition isn't enough. Why? Because the examiners target very distinct cognitive domains, which we call assessment objectives. First up is knowledge and understanding. This is your basic recall. Do you know what EMF stands for? Can you recite Lenz's law? But they won't stop there. The second domain is application to unfamiliar contexts. They're not just going to give you a standard bar magnet and a copper coil every time. They might throw a rotating turbine in a massive hydroelectric dam at you, and you have to apply those exact relative directions of force, field, and current to that totally new situation. Finally, we have critical analysis. This means evaluating evidence, finding limitations in an experiment, and making justified recommendations. Conquering all three of these domains is how you lock in that top grade.
Section 2. Procedural Framework. Let's move from theory straight into execution.
And this brilliantly illustrates exactly how to tackle complex induced current problems systematically. We call this the DESET methodology. It's a 5-step procedural framework. Step 1, deconstruct the question. Literally underline the command words. Are they telling you to state, describe, or explain? Step 2, extract relevant data. Pull out all the numbers, the directions, the variables. Step 3, select your analytical framework. For this specific topic, that almost always means grabbing Lenz's law or the right-hand rule. Step 4, execute with clear notation. Write your steps out logically. And finally, step 5, present with correct terminology. You never write "the power gets bigger." You say "the magnitude of the induced EMF increases." This systematic, step-by-step analysis is exactly what separates a top-tier candidate from everyone else. Now, to execute that final presentation step perfectly, top students rely on the PEEL framework to structure their extended responses. Point, evidence, explanation, link. You make your primary point, let's say stating the direction of the current. You then provide evidence, maybe identifying the direction of motion from the diagram. Next, you offer an explanation using actual physics principles, specifically bringing up Lenz's law and the opposition to the change in magnetic flux. And finally, you link it all right back to the specific question they asked you. Before we continue, subscribe to our YouTube channel Ace the Exams at acexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Now, take a look at the mark potential when we apply this. Remember Alex and Sam's flawed answers from earlier? Alex's totally unfocused knowledge dump and Sam's rushed, incomplete sentence. Their mark potential sits at a staggeringly low 20 to 30%. They're quite literally throwing marks away. But the very second we transform those exact same answers, processing them through the DSET methodology to get the right data, and then structuring the written response using the PEEL framework, we see an immediate massive jump. The mark potential rockets all the way up to 100%. You aren't actually learning new physics here. You are just learning how to translate the physics you already know into the exact language and structure the mark scheme demands. It's a total game changer.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams at acexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. Section 3, Critical Analysis. It's time to develop the evaluator's eye. Let's move to and see how this builds into a continuous, unbreakable cycle. The examiners actually outline a highly specific problem-solving loop that you absolutely must internalize. It kicks off with deconstruct, identifying the given information and breaking a really complex physics scenario down into logical, bite-sized steps. Then you move to solve, where you work the problem systematically using your equations and frameworks like PEL. But the most crucial step, and honestly the one almost everyone skips, is evaluate. Evaluating evidence means checking your answer for reasonableness. If your calculation spits out that an induced current is 5,000 amps and a tiny little copper wire, well, your evaluation step should be screaming at you that something went wrong.
Okay, let's put this into practice with a 60-second data scan challenge. Look at this complex data mapping the speed of a magnet falling through a coil against the measured induced EMF. What exactly is the examiner trying to hide in this data? Your data interpretation skills here are absolutely critical. You have to extract the numbers, sure, but more importantly, you must interpret the relationships. Notice how as the speed doubles, the induced EMF doesn't just randomly increase, it scales proportionately. But check out the polarity column. It completely flips the second the magnet exits the coil. Drawing evidence-based conclusions from raw data like this, while under intense time pressure, is exactly what separates the A-star candidate from the B candidate. You have to train your eyes to see the physics story hidden inside the grid of numbers.
Let's play Find the Flaw. We're going to compare generic versus context-specific answers. The generic approach might read, an EMF is induced because the magnetic field is cut, and Lenz's law says it opposes the change. I mean, it sounds true, right? But it bleeds marks. Now look at the context-specific answer. As the north pole of the bar magnet enters the copper coil, the coil cuts the magnetic field lines, inducing an EMF. The induced current creates a north pole at the top of the coil to oppose the downward motion of the magnet. Do you see the massive difference there? The generic answer just parrots the textbook. The specific answer uses the exact materials and directions provided in the scenario. Examiners note this time and time again. Candidates lose precious marks simply because their answers aren't specific to the context given.
All right, it is time for a 30-second mental speed writing challenge. I want you to craft one perfect, single PEEL paragraph explaining the relative directions of force, field, and current for a wire pushed downward through a horizontal magnetic field. Ready? Start deconstructing. What is your point? State the direction of the current. What's your evidence? The downward physical force. What is your explanation? You bring in Fleming's right-hand rule or Lenz's law principles of opposing the motion. And finally, link it back. By practicing under these intense micro-time constraints, you build the muscle memory you need to effortlessly deploy the PEEL structure when the real exam clock is ticking down.
Section 4, Top Examiner Warnings. We are going straight inside the Principal Examiner Reports.
Here are the top 3 mistakes cited directly by the examiners themselves. Number 1, using the wrong approach for the context. This is the absolute classic trap. Students see a coil, and they immediately start using Fleming's left-hand rule for motors instead of the right-hand rule for induced generators. They apply the completely wrong conceptual framework. Number 2, forgetting to check format and presentation. This means sloppy handwriting, forgetting your units, or not clearly annotating diagrams when they literally ask you to show the direction of the induced current. And number 3, which we just hammered home, providing answers not specific to the context given. If the exam question is about a massive wind turbine, your answer absolutely cannot be about a tiny laboratory bar magnet. You have to synthesize your core knowledge with the precise scenario sitting on the paper in front of you.
To combat all of these mistakes, we use the Physics Success Blueprint. These are the 3 absolute rules that synthesize everything we've covered today, and they practically guarantee top marks. Rule 1, command word decoding. Never ever start writing until you know if you are stating, describing, or explaining. Rule 2, Peel framework application. Structure every single long answer with point, evidence, explanation, link to ensure you hit every assessment objective. Rule 3, time management matrix. Allocate your time strictly based on the marks available. Please don't spend 5 minutes on a 1-mark recall question, and don't rush through a 4-mark application question. This blueprint is your ultimate weapon in the exam hall.
The data truly speaks for itself. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Moving up the grading scale is entirely possible when you stop fighting the physics and start playing the exam game intelligently using these structured frameworks.
Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSEs and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here. I want to leave you with this ultimate safety net, pulled directly from an examiner alert. Students lose marks by not showing working. Even if your final answer is wrong, method marks can save you. Think about that for a second. In the incredibly high-stakes environment of the exam room, your procedural framework, your systematic analysis, your DSAP and Peel structures, these are your shields. Is it possible that your clear, logical process is just as important as your final answer when it comes to demonstrating your understanding of the physics of our universe? Show your working, trust the framework, and I will see you in the next explainer.